Hi everyone. So in this lecture we are wrapping up our discussion of descriptive statistics, which is chapter 2. We talked about measures of central tendency and measures of variation. Now we're going to talk about measures of position. And by that we're going basically, where in position of a particular data entry inside of a data set, if a data set is ordered from the minimum to the maximum. So first we'll talk about quartiles, and then we'll move to percentiles. So a quartile is just what you think. We divide the data set into approximately 4 equal subsets, 4 equal parts, and they're separated by these 5 numbers. The maximum, then we call it the third quartile, which we call Q3, and the median, which is of course the middle value, the Q1, which we call the first quartile, and then the minimum. So basically we have all the data entries between the minimum and Q1 is the bottom 25%. Between Q1 and the median is the second 25%. Between the median and Q3 is the next 25%, and then between Q3 and the maximum is the top 25%. Okay. Just like the median, the actual values of Q3 and Q1 do not necessarily have to be actual data entries. Okay, they are just markers to indicate, to break up the data set into 4 equal parts. We define the inner quartile range as basically the middle 50%, and that or at least it indicates it represents the middle 50%. What it actually is just a single number. It's the difference Q3 minus Q1. So basically it's the distance from here to here. And then now we talked about outliers, and here's the technical definition. So we know that an outlier is a number that is far from the other entries. Well, just how far? Well, it's either less than this number, Q1 minus 1.5 times the inner quartile range, or it's more than this number, Q3 plus 1.5 times the inner quartile range. And then by this all combined, these 5 numbers, the minimum, Q1, the median, Q3, and the maximum, that's the 5, what we call the 5-number summary, and it can also be represented by something called a box and whisker plot, where we plot on the number line, we plot these 5 numbers, and we draw a little box to indicate the middle 50% of the data entries. So just as an example how we do this, the good news is we don't have to compute this by hand, but I just took this data set of 17 entries and I reordered it. By the way, we can clearly see what the outliers are. It would be 25 and 80, right? Because all the other numbers are between 50 and 60, and or 65. So the good news is we can use our calculator to do this. So what I've done is here's our stat, edit, and in L6 here I've entered these entries. Oops, and I don't know if you can see that. Hopefully you can't. Okay. You have these entries. So we'll go back and we will hit stat again, and we'll go to select calc, first variable stats, and we'll do L6 because that's our column. And okay, this time we're going to scroll down, and we can see that our this is our 5-number summary right here. We can see the minimum is 25 and the max is 80, which we already knew, but we get that the median is 60, Q1 is 56.5, and the Q3 is 63 exactly. Okay, so yeah. So let's see so maybe we'll just write this down. So the min is 56.5. Q1 is, we said, is 56.5. Okay, and that's about right here. And the median, we said, is 63, or rather 60, and looks like it's going to be about, we can put this 60 right here. So that, in this case, because we have an odd number of entries, we can, the median is actual a data value. Q3, we said, is 63. Okay, so it's about right here, and the maximum is 80. Okay, the interquartile range would be 63 minus 56.5, right, which is 6.5. And the we can clearly see that what the outliers are, because if we compute Q3 plus Q3 is 63 plus 1.5 times 6.5, this turns out to be oops, I think I messed up on my notes, so I'll just do this real quickly. So alright, so that's 72.65 or 72.75, and then if we had take 56.5 minus 1.5 times 6.5, this would be 46.75. Okay, all right, and we can see that 25 is certainly less than this number, and 80 is bigger than this number. So our outliers would be officially 25 and 80. Okay, so that's how quartiles are. Percentiles, maybe you've heard of these before, and it's just basically to clear up some of the misconceptions. So if you have a if X is a data entry, we say the percentile of X is the number of data entries that are strictly less than X divided by the total number of entries, and then that fraction is multiplied by 100. Okay, and we round to the nearest whole number, so it's always an integer. So if you get a score and your score is in the 90th percentile, that means that 90% of the scores were strictly lower than your score. Okay, we don't count any people who had your score. That's included in the upper 10% with you. Okay, so so with that in mind, we have here's a data set, and if we just wanted to find what these percentiles are, the percentile of 36, and by the way, it really doesn't matter if these numbers are in the data set or not. 36, how many are less than 36? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this would be 12, and there are a total of 27 entries here. So 27 data entries. So we multiply that by 100, and this turns out to be 44. So that would be the 44th. The score of 36 would be in the 44th percentile. Percentile of 49. Well, we just have let's go to 42. Let's keep. Did these out of order. Actually, we might as well do them in order. So 49. How many entries are less than 49? We have 9 here, 18, 19, 19, right? So this would be 19 out over 27 times 100, and average this out, and this turns out to be 70 percentile for 42. How many numbers are less than 42? Well, we have 9, 10, 11, 12, 13, 14, 15, 16. 16. There is no 42 here, but 41 is less than 16. So this would be 16 over 27. 7 times 100, which is 59. Okay, so that's really all there is to percentiles. And the percentiles are sort of a generalization of quartiles, where we chop the data set into 100 parts instead of just 4. Okay. Then another way of talking about position of a data entry are z-scores. And with z-scores, you have this. It's the position with respect to the mean and standard deviation. This is when those come into play here. So we say if a data set has a mean mu and standard deviation sigma, and x is a data entry, the z-score of x is defined to be the quantity x minus mu divided by sigma. So basically it's the derivation of how far you are from the mean divided by the standard deviation. And it basically is a z-score is basically the number of standard deviations from the mean, where of course this number doesn't have to be a whole number. Most of the time it won't be, but a z-score of 0 would mean that you are at the mean. A z-score of 1 would mean basically you're talking about the number mu plus sigma. A z-score of 2 would be mu plus 2 sigma. A z-score of -1 would be mu minus sigma. A z-score of -2 would be mu minus sigma. And I would just remind you that data scores are data entries would be unusual if they're more than 2 standard deviations. So we would say an unusual z-score would be either when z is less than -2 or when z is greater than 2. Okay. All right. So if I ask you for a z-score, I have to give you either the mean and the standard deviation, or you have to compute that yourself. So let's say in this example we have a data set that has a mean of 14.3 and standard deviation of 3.5. We just plug this into this formula up here. So z would be, so basically in this case we're saying this is mu and this is sigma. So our z-score would be, and our data entry is 10, so it's 10 minus 14.3 divided by 3.5, okay, which turns out to be -1.23. Okay, and with z-scores you can get away with just rounding 2 decimal places. Okay, in this case, if x is 16.1, the z-score would be 16.1 minus 14.3 over 3.5, and this would be 0.51. Okay, now what happens if you're given z and you want to find what the actual data entry is? What is x? Well, you just have to do a little bit of algebra. Okay, and I wanted to do this because I like algebra, and there's very little algebra in this course. But to find out what x is, you can just first multiply both sides by sigma. Okay, and then add mu to both sides. Okay, and so clean things up, and you get that x is going to be mu plus z sigma. Okay, so that's basically converse of this. Okay, so in this case, x would be mu, which is 14.3, plus 1 times sigma, which is 3.5. Okay. And this turns out to be 17.8. In this case, if x is going to be z is -0.6, this would x would be 14.3 plus negative 0.6 times 3.5. We plug this in our calculator and we get 12.2. Okay, and in all four cases here, none of the data entries are unusual because all the z-scores are between -2 and 2. This is going to be very important because when we get into to talk about distributions, we'll be using a standard normal distribution. And that's going to be a distribution where the mean is 0 and the standard deviation is 1. And any distribution, if we take a data set with any mean and standard deviation, we can do some little mathematics and substitution and reduce a problem to being reduced to a something called the standard distribution. And that again is because of z-scores. So we will talk about that later. We'll do a lot of fun stuff with that next time when we talk, well, in the future in Chapter 4 and Chapter 5. But in the meantime, we got some nice hard-hitting stuff with probabilities for the next chapter. So hopefully you're looking forward to that just like I am, and I will see you next time. Take care.